All right. So today we are starting chapter 4, which is called An Introduction to Probability. Probability, there are 3 different types of probability. We're really only going to discuss one in detail, and then I'll show you an example of another type of probability, but they're all calculated the same way. So probability is calculated as success over total. All right, so probability is success over total. Now, success is going to change depending on what you're looking for in your problem. Oh, and we are going to need calculators, so if you don't have a calculator and you need one, then grab one. So success is going to change based on what you're looking for. If you're looking for whether someone smokes, if you're doing a survey about people that smoke, then a success would be someone that smokes. So not necessarily positive. Don't think of success as being something positive. It just means that you found what you were looking for. And the total is calculated using what we call the fundamental principle of counting. So the fundamental principle of counting, which is pretty easy to use. It just involves multiplication, so nothing fancy there. All right, so the first thing I wanted to tell you the 3 types of probability. So the 3 types of probability, we have classical. This is going to be your typical problems like you roll a dice, what's the probability of rolling a 4? All right, so classical probability, those are calculated using formulas. Then we have experimental probability. That's where you're looking at the probability using some data that you collected through a survey or some kind of study. All right, so that's just using data from a sample. So experimental probability using data from a sample. And then lastly, we have subjective. That's the one that we're not going to talk about today because your book says, you should be wary of subjective probability. This is where people are making educated guesses based on their knowledge of the subject. So they're saying like, oh, I watch the stocks all the time, and I know that Facebook stock is about to go down. So they don't have any data to back that up. They're just saying like based on their experience that's what they believe to be true. All right, so we're going to be identifying outcomes in a sample space or an event. Let me tell you what a sample space is. A sample space is just a set of all possible outcomes. So the sample space is the set of all possible outcomes. So if you're rolling a dice, then all the possible outcomes would be like rolling a 1, rolling a 2, a 3, a 4, a 5, or a 6. So that's just where you list out all the possible outcomes. An event is a specific scenario. So if you're rolling a dice, maybe you're looking for an even number. You want to roll an even number. So that would be your event, that you roll an even number, or rolling an odd number, or rolling a prime number. So it's just some specific scenario that you're looking for. All right, so let's look at our examples. I think you're gonna find these are pretty easy. This one says, write out the sample space for the given experiment. Use the letter H to indicate heads and the letter T to indicate tails. 3 coins are tossed. All right, so we've got 3 coins. Each one can be heads or tails. We're going to list out all the possibilities for what we could get if we toss these 3 coins. So starting off with the most basic ones, we could get heads for all 3, or we could get tails for all 3. All right, so let's build off of that. All right, so give me another possible outcome that starts with heads.
Heads, tails, tail.
Heads, tails, heads, or which one was the last one? I guess it doesn't matter. Heads, tails, tails. What's another one? Heads, tails, heads. HTH. I think there's one more that starts with heads. HHT, good. All right. And what about for tails? Starting with tails. Tell me another outcome that starts with tails.
THH.
THH.
THT.
THT. And then one more. TTH. Now, how many outcomes have we listed here? 1, 2, 3, 4, 5, 6, 7, 8. Right?
Yeah.
All right, so I'm going to show you how to check and make sure that you've got all of them. All right, so we've got 3 coins, right? How many options do we have for the first coin? What could we get whenever we flip the coin?
We got 5.
We could get heads or tails, right? So how many options are there for that? 2. What about for the second coin? 2. What about for the third coin? 2. All right, so then the fundamental principle of counting says you just multiply those. So you just multiply those, that's by the fundamental principle of counting, and that's gonna tell you how many outcomes that you should be looking for. What's 2 times 2 times 2? 8. So that means we got all 8. All right, now, your homework, if I remember correctly, they're gonna want you to write this out as a set. So you're gonna wanna do like a curly brace, and then write all of your outcomes separated with a comma. So HHH, comma, HTT, comma, HTH, comma, dot, dot, dot. So you just continue on that pattern. Fill in all your outcomes and then close your set with a curly brace. All right, so fundamental principle of counting, it just helps us check our work, just making sure that we have all of the outcomes listed. If we had checked our work with the fundamental principle of counting and we only had 6 outcomes listed, we would know that we had 2 more we needed to find. All right, everybody good? All right, let's do the next one, which is where you're a server at a restaurant, and this is, you're taking people's orders for their salad. All right, so it says write out the sample space for the experiment. Use O for olive, C for cucumbers, H for ham, P for pepperoni, R for ranch, I for Italian. You're the server at a restaurant. Your customers are deciding what they want to put on the salad. Their choices are that they can choose 1 topping, olives or cucumbers, 1 meat, ham or pepperoni, and then 1 dressing, ranch or Italian. So we have topping, that's 1 choice. Then we have meat, that's another choice, and then dressing. How many options do we have for toppings? 2 for meat
2.
and dressing?
2.
2, so 2 for each. So we should have how many outcomes total? 8, good. 2 times 2 times 2 is 8. All right, so we need to get 8 outcomes in total. That just is gonna help us make sure that we get all of them. So let's write out the sample space. Do your little curly brace. Let's start with olives. So you could have olives, ham, ranch. Olives, ham, ranch. All right, tell me another option that starts with olives.
OHI.
OHI, olives, ham, Italian.
OPR.
Good, OPR. Olives, pepperoni, ranch.
OPI.
OPI, olives, pepperoni, Italian. Is that everything with olives?
Mm-hmm.
Yeah. So now we're going over to the other topping choice, which is cucumbers. So you can kind of use this as a template. You could do CHR, CHI, CPR, CPI. So that way it saves you some brain power. So just copying the other choices, but now with cucumber. Cucumber ham ranch, cucumber ham Italian, cucumber pepperoni ranch, and then cucumber pepperoni Italian. Did we get all 8? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. All right, so once you've got all 8 written down, you can close your curly brace. We good? These are not bad. Especially if you use this fundamental principle of counting. That's what this is. Fundamental principle of counting. So if you use the fundamental principle of counting, it really helps you make sure that you've got all of your options covered. All right. Now we're going to get into actually calculating probabilities. Just as a heads up, probabilities are always between 0 and 1. So they're either going to be a fraction or decimal. Probabilities have to be between 0 and 1. So if you get a whole number for a probability, then you know you did something wrong. Or if you get a negative number for a probability, you know you did something wrong. These should always be fractions or decimals that are in between 0 and 1. Okay, so what is the probability that a randomly selected person will have a birthday in March? And then it says, assume this person was not born in a leap year, express your answer in simplified fractions. So how many of y'all in here were born in March? Anybody got a birthday in March? Nobody. All right, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of 16, there's 0 people with birthday in March. That would be an experimental probability. So if I'm just using the people in this room to calculate the probability, that's an experimental probability. We're going to calculate this using classical probability. So it's success over total. So probability equals success over total. How many total days are there in the year? 365, so that's our total. How many out of those 365, how many of those days are in March?
I think
31.
31.
Good, 31. And that's it, you're done. So the other option that you might have tried to approach it this way is to say, okay, there's 12 months in a year, only one of those months is March. But don't do that approach because not all the months have the same number of days. So you want to do it using the days approach. That way we capture all 31 of those days. All right, so let me show you how to check and see if this is simplified. So you're just going to grab your calculator. 31 over 365. You're going to type that in, 31 divided by 365. 31 divided by 365. You can go ahead and hit enter. That's the decimal version. Now, Hawks will accept the decimal version of the answer, but they just want it to like several decimal places, like 4 or 5 or 6. So I think writing it as a simplified fraction is a little easier. So you're just going to hit the math button and then the first option, which has the little triangle and then frac, that means convert to a fraction. And that's always going to return to you a simplified fraction. So it already was in simplest form, 31 over 365. So that's just checking to make sure that we are in simplified form. Okay. Everybody good with this one? How would this change if it was like, what's the probability that someone has a birthday in November? Be 30 days in November. So it'd be 30 over 365. So it's just going to change based on the number of days in the month that they tell you. All right, a coin is tossed 6 times. What's the probability of getting all tails? All right, so the tricky part here is to figure out, we're using classical probability, so we got to do success over total. The tricky part here is figuring out what the total is. but we're gonna use the fundamental principle of counting, to figure that out. We have one coin and we're tossing it 6 times, so this would be like toss number 1, toss number 2, 3. Naturally, I haven't given myself enough room here. Okay, 3, 4, 5, 6. All right, and then in each one of those boxes, we're gonna write how many choices we have. So when we flip that coin the first time, what are my 2 options? Heads or tails, right? So I have 2 possible outcomes. All right, so 2. What about for my second toss?
Hesitant.
Yeah, two outcomes, heads or tails, heads or tails, heads or tails, heads or tails for each one. Right now, if I multiply these out, that's gonna tell me my total. So what's 2 times 2 times 2 times 2 times 2? I think I said that. 64. This is also 2 to the 6. That makes it a little easier to plug in. All right, so that's our total. It's not our answer. Can't be our answer, right? It's a probability. It has to be between 0 and 1. So that can't be the answer. It's the denominator. All right, so 64 is the denominator. Now, there's only one way you can get all tails. There's no separate way to get all tails. So there's only one way to get a success. So that's your answer. So only one way to get all tails. Now, if they had said, what's the probability of getting 2 heads, that's a lot more involved. You would have to write out all 64 possibilities and then pick out how many had 2 heads. But this one is unique. There's only one way of getting all tails. Same with all heads. There's only one way to get all heads. So that's our answer. And then, of course, this is in simplest form because our numerator is 1. All right. I think that's the hardest one out of these. The rest of these are pretty straightforward. All right. What's the probability of rolling a sum of 5 on a standard pair of 6-sided die? All right, so the key word here, and I almost rephrased this because I don't think that it worded very well, but this is the key word here, a pair of 6-sided die. How many dice is that? 2 dice. All right, so a pair of dice would mean 2 dice. So there's our first dice, there's our second dice. Now, how many, when I'm rolling a dice, it says a 6-sided die. So I have 6 options for what I can roll. I can roll 1, 2, 3, 4, 5, or 6. Right, so I have 6 options on this first roll. What about for the second dice?
You got 6.
6. So what is my total?
36.
Good. So when I'm doing success over total, I know that my denominator is 36. All right, now we have to think of, if you're rolling a dice, what's all the ways you could have those numbers add to 5. All right, so you could have a 1. So here's dice number 1, here's dice number 2. You could roll a 1 and a 4. What else could I roll to get a sum of 5? 2 and 3. Now these dice are unique, so you also have to consider the opposite. So a 4 and a 1 and a 3 and a 2. 4 and 1, 3 and 2. What about, can I roll a 5 and a 0? No, there's no 0 on a dice. All right, so there's nothing else that adds to 5, right? Y'all think of anything else? That's it. The higher the number, the more choices there are. So if you said like a sum of 7, the list would be longer. All right, but there's only 4 out of the total 36 outcomes. There's only 4 ways to roll a sum of 5. So that's my successes. So there's 4 ways that I could roll a sum of 5. Now this can definitely be simplified because I know 4 goes into 36. So try on your calculator and tell me what that is simplified. 1 over 9. Good. And again, you can write this as a decimal in Hawks, that's totally fine. I just think it's easier to keep it as a fraction, so you don't have to keep up with all those decimal points. All right, we have one more classical probability, and then we're going to do an experimental probability. All right, a box contains 51 red marbles, 14 white marbles, and 81 blue marbles. What's the total number of marbles in the box? 146. So 146 total. If a marble is randomly selected from the box, what's the probability that it is red? All right, so success over total. Total we said was 146. What's my successes?
What?
51?
Yeah.
Yeah, because that's the number of red marbles. Right now we need to check and see if that simplifies. I don't think it does.
No, it doesn't.
No, okay. Now, I was thinking yesterday about how could they make this harder on Hawks. The only thing I could really come up with is, this is an extra, the beginning part of this slide is the same. But I thought they could ask you, what's the probability that it's not a certain color? So what's the probability that it's not blue?
You add red and white.
Yeah, you would add up the red and the white. That would be your success, would be getting something that's not blue. All right, so success
Thank you.
over total would be, how many not blue marbles are there? 51 plus 14,
65.
65. Total is the same. So that's the only way I could think of that Hawks could make this potentially more difficult, but I think as long as you're paying close attention to the wording, then you should be fine. All right, we have one last problem that is experimental probability. This is where they're giving you, it looks like a little frequency table here, and you're going to answer, or you're going to calculate the probability based on the data in this table. All right, so let's make a little note here that this is experimental probability. Now, it's still calculated the same way, still calculated as success over total. It just gets a different name since we're working with real data. All right, so it says a telemarketer's computer selects phone numbers at random. So they've got some kind of database of phone numbers, and they're randomly choosing, that my number is definitely in there, because they be calling me. And they're gonna select these phone numbers at random, and then they're gonna record the age bracket for the people that answer the phone. All right, so 20 people answered that were under 18. 29 people answered that were between 18 and 25 years old, and so on. What's the probability that the next respondent will be between 18 and 35? So first thing you need to do is figure out the total.
194.
How much?
194.
194? All right, so 194 people answered the phone. So we're still calculating this as success over total. How many people answered that were between 18 and 35? That's
65.
65? So 29 plus 36 gives you 65. Total is 194. Does that simplify? I don't think so. No. All right, so it's still calculated the same way. There's nothing you need to do differently. Whenever it's experimental probability, I just wanted to point out that they do give it a different name. All right, let me stop the recording and then we'll finish up.